Right, so what we have, two reactions at A and B. We've got a rope hanging between, and we've got a load that is attached at C and D. So it's quite a simple setup, and then you've got your dimensions between A, C, C and D, D and B. Then you've got your vertical dimensions. The rope is always in tension, it's never in compression. There are no moments within the rope itself. There's a few assumptions that you've got within your notes. So we've got tensile loads only, so there's no loads pulling upwards, which would remove this rope from tension. Each cable or each rope is assumed to be straight, and also it doesn't stretch. Okay, so that all of the geometry is based upon a cable of a fixed length. And this can be applied to like cable stay bridges. And we've got a few examples of where this can be used. All of our loads will be acting downwards, so it'll just be acting in gravity. We won't be doing any in this module of loads being pulled off to the side, just because then it starts changing the geometry of the cable, and it just makes the calculations more complicated. So within this module, all of our loads are just coming straight down, and they don't extend at all. So let's just assume that it's a high tensile steel. If you have any books, this is from one of the books. I think this is from Seward. This is an example where you have some people on Everest, and there's two people holding up somebody who was fallen. So we've got a cable, AB and AC. And in this example it says, what is the tension within the rope AB and AC based upon this person here weighing 736 newtons. So you can see how you can take the real life example, split it down into a free body diagram, and then from that you can then analyse that using vectors. Most people seem to be able to grasp the vectors in the assignment, which is great. So if a climber is suspended from a rope, so they're 75 kilograms. So first find the force coming down from the person. So it's 75 times by gravity, which is our 9.81. So this is where we got our 736 newtons from. Then based upon the dimensions of the rope, you have 2 by 2, so you have a 45 degree there. And then you've got 2 by 4, so you've got 63.4. So it's easy to work out the angles. Let me just remind myself what you've been given. So on the second page, you've got all of that information. So with our 45 and our 63, you can then 180 take away both of these will give us this angle, and then you've got this angle here is opposite of there, so it's 45, so that's 45. So I'm just giving you theta 1 to theta 4 in order to resolve forces horizontally and vertically, or in the example that we've got here, where we're resolving perpendicular. You don't have to do this, like, you know, if you go through this, there's no reason why you can't do horizontal and vertical. But in this example, we are resolving across this line here. if you resolve about this line, you remove AB, so therefore you have your known 736 and you've got an FAC. Personally, I find it very awkward resolving perpendicular. It's I would probably sort of turn the page around so that I can see everything into a horizontal and a vertical, because whilst it's easy to work out, the common problem is people will get confused with what angle they're using. So again, you're quite happy to work out horizontal and vertical, but for this example, it's resolving perpendicular in order to remove AB. You could afterwards resolve perpendicular to FAC to work out what AB is. So resolving perpendicular, we've got our FAC FAC, and then from this line here we've got 71.6, so we've got the sine of that equals our 45, sine 45 times by our 736. So our FAC is 548. Very simple example. Got FAC, then resolve vertically. So what have we got? We've got our 736 coming down, so we could say that that's positive, and negative you've got FAB, sine 45, and FAC sine 63.4. So it's just a little bit of review of vectors. Okay, so what we have, we've got a cable, and again these cables do not extend, so therefore you can rely upon these dimensions. So we've got our two reactions at A and B, and it's pinned. Now when it's saying it's pinned, like if there was any moment applied with this sort of ground material here, none of that moment would be transferred into AC. If there was some form of twist in a rope, then that will not be transferred into BC. So there's no movement. So all the nodes are considered as pinned. Now first what we'll do is work out what the angles are. Then we'll find out what the cable forces are about C. And there's no steps to, or especially when you've got a longer cable, there's no specific steps on what order you have to analyse this. Personally, I like to take moments around the reactions first, so take moments around A to get my formula for B, take moments around B to get my formula for A. But you'll find that you will have to take moments around another point within the cable in order to work out what the reactions are. Once you've got the reactions, then you'll see that you can actually work out what the forces are within the cables. So first we'll find the angles. So alpha, if you do the inverse tan of 1/3, gives us 18.4. And similarly, B, inverse tan of 1/2. And if you analyse point C, so here's my free body diagram. That's my cable. BC. That's my cable AC. I can draw in my assumed arrow directions. So it's the same as when we were looking at trusses, that you've got a force pulling downwards, therefore there needs to be forces upwards to make sure that this point C doesn't move, that it's in equilibrium. If you've got an arrow pointing towards the middle of the cable, you'll have an arrow pointing inwards there, and both arrows pointing inwards is tension. So it's the resistance of the cable to the forces pulling it apart. So the arrow directions are easier within cables. So we can resolve forces, and again, personally I find it's easier just to do it vertically and horizontal. However, to remove a force, we can resolve about that force. For example, if we resolve perpendicular to BC, we will remove BC from the equation. So we'll say that everything going to the top left is going to be positive. So we've got our AC cosine 45 that's positive, and then we've got coming downwards, you've got minus 10 cosine 26 degrees. And all of that equals 0. AC is 12.6 kilonewtons. So we've resolved perpendicular to BC in order to remove it. So we've got our AC cosine 45, and we've got our 10 force acting that way is cosine 26.6. Then after this we'll resolve horizontal. So we've got a 12.6 AC, we got our BC, and because we're resolving horizontal, we're ignoring the 10 that's coming straight down. We've got BC, cosine 26.6. Minus AC, cosine 18.4. So we're seeing that everything going this way is positive. And all of that equals 0. BC is 13.4 kilonewtons. Very much feels like vectors when you have such a small cable.